today's top point is Smart HVAC begins with Smart HVAC design. So it is honored to be here with all the dignitaries. Thank you so much, Thermal Control Magazine, for giving this opportunity to me. As an industry expert, designing MEP system, and especially when you have, platform like this, we consultant, can showcase our expertise, how, smart HVAC or smart MEP design can contribute to a greener, smarter world. So to begin with, we'll start with my next slide, that is introduction. So, importance of smart HVAC in today's high performance buildings. So, with rising energy cost, stringent government regulations, increasing occupant comfort demand, the HVAC system are no longer just about cooling or heating. Okay, they must be intelligent, adaptive, and efficient. The smart HVAC solution, integrated with the real-time data, predictive controls, and automation. This requires, a lot of design input, optimizing your energy use, your indoor air quality, occupant comfort simultaneously, because that is the key point to achieve. Your occupant should be comfortable. So this is importance of smart HVAC system. So what is the role of MEP designer as a backbone of smart HVAC system or smart systems? MEP design provides the infrastructure and logic that makes the system, or rather say HVAC system operations smart and efficient. So from starting with precise heat load calculation to Deepak sir just said, right IoT sensor or sensor placement and control integration. The MEP design ensures the smart system are technically feasible. It is just not on the paper. It is technically feasible at the same time, cost effective and future ready. Because whatever we are designing today, as Mr. Deepak said, it should be future ready for IoT integration or AI integration. So that is the role of MEP consultant. That whatever you are designing, it should be future ready. A well-planned MEP framework, enables the seamless integration with building management system, IoT devices, and data analytic platforms. So start right from beginning, all these parameters, should be taken care. The objective of this session is, I'll showcase the real data-driven MEP design decisions which we have taken in our past project, which empowered us, to simulate the tools which delivered, measurable performance improvement in HVAC system. In that method, that blends with the engineering principle also and intelligence design also for better building performance and definitely life cycle value. So we'll focus on real case study, which is our diamond manufacturing facility. Uh, Total area is somewhere around 225,000 square feet of manufacturing area, where we have implemented real world high precision manufacturing environment, where somewhere their temperature requirement, RH requirement is 18 degree, 40% RH. Somewhere it is comfort cooling 24 degree. So from variety of temperature and humidity and air purity requirement, which affects definitely production, and worker comfort. So considering all these complex parameters, this project serves as a practical example of how simulation or precise data input or precise calculation, can design and solve this complex problem of reduce energy footprint, maintaining stringent indoor environment, at the same time, fulfilling all the comfort that user requires. So moving to next slide, how data-driven approach, we can achieve this. So whenever we start, we begin the design process. This advanced simulation tool like HAP are the right, tool. There can be other platforms also, but we are using HAP, so I'm using HAP word from the concept stage. So whatever you are designing is with precision. Okay, This design ensures that every MEP decision, especially for HVAC sizing, is backed by the accurate data-driven insight instead of just rough heat load estimates or heat load calculation using rule of thumb. Early simulation can also help identify optimization opportunity. When you are planning your system well in advance, you always have opportunity to look at the data and you can analyze and you can always optimize. So before the drawings are frozen, your design is finalized. Uh, Next is area-wise occupancy and equipment load and envelope input. So the model is built using this. I'm talking about whatever project we have already designed. So the model is built using precise zone level data. So each different zone have different HVAC air conditioning requirement. Covering occupancy density is also different for different area. Equipments are different for different areas, and characteristic of envelope is also different. Like wall, roof, glazing, performance are also different. So this granular input ensures each space is designed, for its actual operational profile, not just rule of thumb or general heat load calculation. Example, we have a laser cutting area where diamond laser cutting machine requires 40% RH and 18-degree temperature inside the machine. Okay, and room temperature should also be 18-degree. So we are providing air conditioning to the machine envelope itself as well as the building, the room itself. So how did we achieve that? So with the iterative heat load modeling, repetitive heat load simulation, instead of just a single run, we follow the modeling process repetitively with the different testing condition, different combination of occupancy, different fresh air requirement, different time zone. Okay, then operational changes. This diamond manufacturing facility are sometimes you have to be the furniture layout or equipment layout. Sometimes technology, since the technology is changing, after 2 years maybe new machine will come. So we have to keep all these parameters in the mind and we have to design the system. So each this iteration moves us to the closer to the ideal, balanced, efficient, and perform design. So literally we have done 50-60 combination of HAP. I'll share you in the subsequent screens. The entire objective is the balanced and efficient system with redundancy at the same time giving comfort to the user. So the key takeaways are, optimized cooling tonnage we could have achieved based on actual usage pattern with precise data received from client, peak load saving through chilled water storage, reduce HVAC related capex opex, and definitely when you are designing the system, you'll have to see the maintenance part also. So maintenance is same in both the models. We have done the groundwork on maintenance part also. Uh, if you are using tank or you are not using tank, the maintenance part remains the same. The only maintenance added is cleaning of your water tank. So, improved controlled via zoning and automation, scalable design for future proofing. So, these are the major design outcome. And client is very much happy with the amount of saving he is achieving. So the whole idea is, if you have perfect data, if you can gather perfect data from client, you'll have to ask a lot of question to client because client sometimes definitely don't have that sort of knowledge as far as MEP design is concerned. So you'll have to literally brainstorm with him for the design input. If you have a proper data, input from client side, from out of your experience, you can derive some data, then you can optimize the system, and all this altogether contributes to a energy efficiency only. So that's all from my side. Thank you so much.